Clausius mathematically expressed the second law of thermodynamics. The Clausius inequality describes how the heat transfer occurring at a particular temperature is related to the amount of irreversibility. It states that for any cycle, the cyclic integral of delta Q divided by temperature T is a negative sigma cycle, which is always less than 0 or equal to 0. Sigma cycle is a measure of irreversibility, so it is how we define entropy. It will be discussed in detail in next chapter. The sigma cycle is greater than 0 for an irreversible cycle processes. The sigma cycle is equal to 0 for a reversible cycle process. And the sigma cycle is never less than 0. The process is not possible. The circle with the integration symbol indicates the integration over the entire cycle. Delta Q is a differential amount of heat transfer at any point. The integration of delta Q is the sum of all the differential amounts of heat transfer over the cycle. And T is the absolute temperature at the point of heat transfer. The Clausius inequality is applicable to any cycle, reversible or irreversible. So now we are going to prove the Clausius inequality. So let's consider a Carnot cycle. So there are two temperature reservoirs. High temperature reservoir TH and low temperature reservoir TC. Let's say there are two different cycles between the two thermal reservoirs. One is reversible cycles. The other one is irreversible cycles. They exchange heat with high temperature reservoir and low temperature reservoir. So both systems absorb heat from high temperature reservoir. So QH is absorbed by reversible cycle. Also QH is absorbed by irreversible cycle. And part of QH will be converted to work. Part of QH will be converted to work by irreversible cycle. Let's say W net prime. The reversible cycle rejects heat QL to a low temperature reservoir. The irreversible cycle also rejects heat QL prime to a low temperature reservoir. So compare the magnitudes of QL and QL prime. The work produced by the reversible cycle is QH minus QL. And the work produced by the irreversible cycle is QH minus QL prime. The work produced by the reversible cycle is greater than the work produced by the irreversible cycle. So we can say that QL is smaller than QL prime. This is based on Carnot corollaries. Now let's see the cyclic integral of delta Q over T. For the reversible cycles, cyclic integrations delta Q over T equals QH over TH minus QL over TL. So heat is transferred from a higher temperature reservoir, temperature TH, and heat is rejected to a low temperature reservoir at temperature TL. So negative sign indicates the heat is rejected from the system. According to the Kelvin's absolute temperature scale, QL over QH equals TC over TH. Or we can rearrange the terms. QH over TH equals QL over TC. And let me change this to TC. So cyclic integrations becomes 0. And this is for reversible cycle. And for irreversible cycles, cyclic integrations delta Q over T is QH over TH minus QL prime over TC. So QH over TH is QL over TC. And rewrite the equations over TC. And from here, we know that QL is less than QL prime. So we know that this values is less than 0. So from this result and from this result, we can write for any cycle, the cyclic integrations delta Q over T is less than 0 or equal to 0. But it is not possible to be greater than 0. Let's say an example. A system undergoes a cycle while receiving 1000 kJ by heat transfer at a temperature of 500 Kelvin and discharging 600 kJ by heat transfer at 200 Kelvin, 300 Kelvin, and 400 Kelvin. So what is the nature of the cycle in each of these cases? We need to determine whether the cycle is reversible, irreversible, or impossible. So here, this is our system. It exchanges heat with two reservoirs. So one is high temperature reservoir at temperature 500 Kelvin. And the system absorbs 1000 kJ, QH, 1000 kJ from the high temperature reservoir. And the system rejects heat to a low temperature reservoir. This is QL, which is 600 kJ. And low temperature reservoir, the temperature is 200 Kelvin or 300 Kelvin or 400 Kelvin. So in each case, we need to determine the cyclic integration of delta Q over T to determine the nature of the cycle. So in each case, let's determine the cyclic integration delta Q over T. So delta Q over T is QH over TH minus QL over TC. So QH over TH is 1000 kJ over 500 Kelvin minus 600 kilojoule. So case A, the temperature of the low temperature reservoir is 200 Kelvin. So this value is negative 1 kilojoule per Kelvin. Case B, cyclic integrations delta Q over T, also QH over TH minus QL over TC. QH over TH remain the same. QL over TC, 600 kilojoule over 300 Kelvin, which is 0 kilojoule per Kelvin. Case C, cyclic integration delta Q over T, QH over TH, QL over TC, 1000 kilojoule over 500 Kelvin minus 600 kilojoule over 400 Kelvin. This is 0.5 kilojoule per Kelvin. So we got negative 1 kilojoule per Kelvin if the temperature of the low temperature reservoir is 200 Kelvin. So this cycle is irreversible. Case B, cyclic integrations of delta Q over T becomes 0. So this cycle is reversible. Case C, so cyclic integration of delta Q over T is 0.5 kilojoule per Kelvin. So this value is positive. So we can determine that the cycle is not possible. So the Clausius inequality describes how the heat transfer occurring at a particular temperature is related to the amount of irreversibility. If the integration value is negative, the process is irreversible. If the value is 0, the process is reversible. If the integration value is positive, the process is not possible.